Hi, in this video I'm going to be walking you through some strategies for approaching a ground-to-ground projectile motion problem, including some helpful tips for organizing your work and knowing how to kind of tackle different situations involved. So to start out, I'm going to just kind of jump right into drawing a picture of the situation, which is a great way to help get acquainted with some of the variables and some of the distances that could be given to you in this sort of problem. So I'm going to draw the situation as I read the problem. So we're obviously starting on level ground because this is a ground-to-ground projectile motion. So I'm just going to do my best to draw some level ground there. And then we're going to start with a football that's just being kicked from one side at an initial velocity that's angled with the horizontal. So I'm going to draw and write this as VI, and this angle right here as theta. And after it's kicked, obviously it's going to undergo kind of a parabolic trajectory before it eventually hits the ground later on down here. And really that's all we can do with that situation. So next is to find the components of this velocity that's given to you. Anytime, and I mean anytime, you are given an initial velocity with an angle, that should be the first instinct, is to use trigonometry to find the horizontal and vertical components of that velocity. The reason you need to do that is because, well, these two directions don't mix. While horizontally, this ball is just going to keep cruising at some constant velocity, at some constant speed throughout the course of the problem. Vertically, it's slowing down to a stop and then beginning to accelerate back down to the ground under the influence of gravity. So over here, I'm going to write, well, Vix is equal to, and Viy is equal to, well, x is all generally 9 times out of 10 going to be associated with cosine of the angle. So we'd be saying the initial velocity times cosine of whatever angle is given to us, theta, is equal to blah, and Vi times sine of theta is equal to blah. So once you run those calculations, you should get about 16.4 meters per second to the right for the x velocity, meaning it's traveling at this speed constantly the whole time for to the right from start to finish. And then vertically, you should get about 11.5 meters per second. And this one does not maintain its direction, but at least initially, it's moving upward. That will change, though, in the second half when gravity starts pulling it back downwards. All right. So after this, really your next step really should be to set up a table to lay out your initial horizontal and vertical information. So I'm going to write this as the y column and the x column, respectively. And in here, it's really just a good idea to write out any information that you could use in order to solve for any of the stuff that you're being asked for. For instance, in the vertical direction, well, we just found a velocity, and in the x direction, we also found a velocity. So Viy right here should equal 11.5 meters per second. And then Vix in the x column should equal 16.4 meters per second. All right. Other things in the y direction that you could take advantage of are the acceleration due to gravity, AY, which would be negative 9.8 meters per second squared. And then finally, kind of a unique feature of a ground-to-ground problem is that it's landing at the exact same height that it starts from. So the vertical displacement from start to finish should be delta y equals 0. Nice. And with that, in the y direction, we have now unlocked all three pieces of information that we need in order to get everything else that we need. So once you've hit 3 pieces of information in a column, just go ahead and stop there and get started on the problem. So let's jump right into that. So part A over here is asking us to figure out what the velocity of the ball just before it strikes the ground is. When it's saying velocity just before it strikes the ground, that's basically saying the final velocity when it reaches the other side of this parabola. Now, another crucial thing is that it's looking for the total final velocity. So you're going to need to ideally invoke some Pythagorean theorem by the end of this. So the good news is half of this question is already accounted for. So we're looking for really the final velocity in the x direction and the final velocity in the y direction. And when we combine both of those together with the Pythagorean theorem, we'll get the final velocity overall. So I'm going to look at the x direction first. And well, the good news is, well, we noted that in the x direction, really the speed isn't changing conceptually. It's going to stay the same throughout the whole problem. So from that alone, we can say v of x is going to equal, well, v initial x, which is 16.4 meters per second. All right. And then for v of y, well, we are going to have to do a little bit more math here. So we have our information and we're looking for final velocity. So we should have final velocity, initial velocity, acceleration, and delta y. So whichever equation doesn't involve time is the one we can take advantage of here. So it's looking like equation 4 is going to work best for that. So we'll go ahead and continue on with that. So let's say vfy squared is going to equal v initial y squared plus 2 times ay times delta y. And if we go ahead and plug everything in here, we've got 11.5 squared plus 2 times negative 9.8 times 0. Which is good for us, because that means this 0 just knocks everything out entirely in that term. And we're left with kind of a strange result here, which is that vfy equals, or vfy squared equals 11.5 squared. So if you were to take the square root of both sides of that, well, you're going to get vfy equaling, well, plus or minus 11.5 meters per second. Now, it's plus or minus because mathematically we don't really know when we take the square root of a value, but physically our intuition tells us, well, hopefully this ball is falling downwards towards the ground as it hits the ground. So we can assume safely it's probably negative 11.5 meters per second. Okay, that's cool. So there's kind of a neat result here that prevents us from having to really use Pythagorean theorem here. And that's that, well, initially we started at 11.5 and vertically, and initially we started at 16.4 in the horizontal direction. So if you notice, our values for horizontal and vertical are exactly the same in the final case as they were at the start. So then if you were to plug these values into the Pythagorean theorem to get the hypotenuse of your final velocity there, you would find that Vf, weirdly, would have to just equal 20 meters per second again, and it would be down and to the right. Weird. But in the context of a ground-to-ground projectile motion problem, it makes perfect sense, because this whole parabola is symmetrical, and gravity is accelerating it at the same rate throughout the whole trajectory. So as this ball travels up to the peak, it then gets accelerated back down for the exact same amount of time, and so its final velocity should match up exactly with what it started at initially. Pretty cool. All right. So next is part B, and I'm going to do this in a different color. I'll do purple. And so for part B, it's asking when does this thing hit the ground? Now, the word when means we're probably looking at solving for a total time here. Now, time is cool because it really applies to both. I'm going to have to move it out to the side here. But time is a very useful information to find because it's going to apply to both directions once we get it. So it's really helpful to solve for that first across the board. So again, we're going to take advantage of our vertical direction here because we have enough information to kinematically solve it. So I'm going to, again, take a look at our kinematic equations here. Whoop. I'm going to say, well, we have initial velocity, we have acceleration, delta y, and time. So we should look for the equation that doesn't involve the odd one out, which would be final velocity here. So that's looking like this one, number 3. And so if we go ahead and translate that into our language here, we're looking at something that's going to be delta y, a displacement, equals VIY times t plus 1/2 times AY times t squared. All right. And now if we go ahead and plug in stuff for that, we should end up with, and I'm going to go ahead and maybe write it down here, 0 equals VIY, which is 11.5 times t plus 1/2 times negative 9.8 times t squared. Cool. And now if we rearrange this a little bit, we can add this term right here to the other side because 0 is generally considered free real estate. And because this term would be negative because of that negative 9.8, we want to add it to the other side. So when we do that, well, 1/2 times 9.8 is 4.9. So we'll do 4.9 t squared equals 11.5 times t. Cool. And when we do that, good thing happens. We can freely divide both sides by t once in order to eliminate one of those. So that's going to get rid of the t squared here and just replace it with regular t. And it's going to eliminate t outright from this right side here. That's good for us because that gives us a very easy way to now solve for t by itself, which is if we divide both sides by 4.9, we should end up with a time of about 2.34 seconds. And if you take a look at the answer down here, well, that's what's expected. So pretty nice. So on to part C. Part C is asking how high does it go? Now how high it goes is really looking at this distance or displacement right here, which I'm going to call h max, just to distinguish it from delta y, which we've already kind of used. So h max is really looking for the point when the ball has reached its highest point vertically and it's coming back down. So if you remember your concepts there, that's going to be where the ball just ever so temporarily reaches a velocity vertically of 0. So let's say the vertical velocity, let's say Vy max or something, at that point is going to equal 0. And we're looking for h max, which is a displacement. So in this case, again, let's just go ahead and take advantage of all the information we can here. Really, instead of delta y equals 0, which really only applies to this point over here, we're going to want to use this new piece of information of this final velocity that it's reached when it reaches the peak. So if we do that, we're looking for something that doesn't contain time in this case, because we don't really know totally exactly when it reaches that point, unless you maybe consider symmetry. So in this case, we're looking for something that has final velocity, acceleration, initial velocity, and displacement. So again, it's looking like number 4 is going to be the way to go here. So let's go ahead and write all that out. So we've got delta y, or sorry, not delta y, h max or hold on. So it's looking like we've got Vy max squared equals VIY squared plus 2 times AY times H max okay. We're really getting crazy with the subscripts here. So Vy max is going to be 0. Then VIY is going to be 11.5 squared plus 2 times negative 9.8 times H max, which is what we are solving for. All right. So then we want to, again, kind of like last time, move this over to the other side because this will be a negative term. So we can just kind of move it freely into the 0 as free real estate. So if we do that, you're going to end up with, well, 2 times 9.8 is 19.6. So it'll be 19.6 times H max equals 11.5 squared. Okay. And if you go ahead and run the numbers on that, then you're dividing both sides by 19.6 there, and you should get a value of about 6.73 meters. Cool, cool. Finally, part D is asking how far it goes horizontally from start to finish. So that's, if I'm color coding it in red here, kind of this line from start to finish, which we're going to call delta x. And so down here, we're finally working with the horizontal direction, in which really there's only one equation you can use. You can say, well, delta x has got to equal the velocity that it's just traveling at a constant rate the whole time, which is Vix times t, which we solved for in part B. So if you go ahead and plug that in, it's going to be 16.4 times, well, 2.34, which should get you a final answer of about 38 meters, rounding up or down a little bit. And really, that's all there is to it. Now, I'd say from start to finish, the main important thing to always make a habit of doing, regardless of what they're being asked or whatever they're asking you to find, is everything to the left of this green line here. As long as you set everything up, you give yourself a good visual, you solve for the components right off the bat, you tabulate everything maybe, or organize it however you see best, everything to the right of this green line becomes a cakewalk to set up and solve. So consider always setting aside a little bit of land for this setup over here, and it will make your life a heck of a lot easier with everything in physics going forward. So with that, that's all I've got for you. Thank you for watching.